Welcome back. In this video we are going to find the null space of a 3 by 5 matrix A given here. We begin with our first step, which is to find the reduced row echelon form of A. We call this U, and we set it equal to the RREF for short. We can do this using the elementary row operations that we discussed in the last video, or we can use a calculator. In any case, we see that the RREF form of A is given by 1, 0, 0, negative 2, 0, 0, 0, 1, 0, negative 1, 2, 0, 3, negative 2, 0. Notice that the dimensions of these matrices are the same. This is a 3 by 5 matrix. This was a 3 by 5 matrix. Also, we note that the first column of U and the third column of U are pivot columns. We see that there are a total of 2 pivot columns. Because we started with a total of 5 columns, we can immediately calculate that there will be 3 non-pivot columns. And this is because the total number of columns is equal to the number of pivots plus the number of non-pivots. The number 3 is special here because this is the number of linearly independent vectors that we want to produce to span our null space. The next step of our process of finding the null space is to identify the non-pivot columns. Well, we've done that right above. In this case, we see that our non-pivot columns are given by the second column of U, the second column, the fourth column of U, and the fifth column of U. As we will see, these correspond to the second column of A, the fourth column of A, and the fifth column of A. Once we've identified our non-pivot columns, what we'd like to do is use linear combinations to produce a zero vector. As we've discussed before, when we mean linear combinations, what we really mean is matrix vector multiplication. Remember, the whole process that we're going through right now is to find the null space for this matrix, and we recall that the null space of A is going to be the set of all input vectors. In this case, those should be size 5, such that when you multiply A by those inputs, we get 0. And that's why we're looking for input vectors that produce a 0 output. Well, my claim is, once we know this information with this form, we can immediately produce the vectors x that send A to 0. Let's see how to do this. We begin by looking at U2, which is the second column. We see that in this case we have the second column of U is written as negative 2, 0, 0, which we can rewrite as a scalar vector multiplication, negative 2 times 1, 0, 0. But we recognize 1, 0, 0 as the exact form of the pivot column U1. Well, all of a sudden we now have an equation that relates U2 and U1, which also means we have an equation that can produce 0. By bringing this over to the other side, we see that 2 times the first column of u plus 1 times the second column of u is equal to the 0 vector. Well, this is a linear combination of the columns of u given by 2 times 1, 0, 0 plus 1 times negative 2, 0, 0 is equal to 0, 0, 0. We can then further expand this by recognizing this linear combination as a matrix vector product. In particular, if we write down the zeros in this matrix vector product, we see immediately that this linear combination includes no terms from the third column of u. It includes no terms from the fourth column, and it also has no scalar weights times the fifth term, and we produce 0, 0, 0. Now if we look at this, what we see is this is the matrix vector product u multiplied by the scalar weights. Well, we knew that the first scalar weight on the first column is 2. Right? So we see that this 2 goes with that first column. The second weight is 1. The third weight is 0 because that's lined up with this one. The fourth weight is 0. The fifth weight is 0. So all of a sudden we see that if we take this linear combination of these columns, we produce the 0 vector on the right hand side. Thus, the first vector in our null space, which we're going to go ahead and call z1, is the vector 2, 1, 0, 0, 0. Let's move on to the next one. We said that the first vector for our null space that we found corresponded with the first non-pivot vector, or non-pivot column. Let's find the next one. Well, the next vector in our null space is going to correspond with the second non-pivot column. In this case, we recall from our initial calculations of the RREF, here was our second non-pivot column. So we see that U4 is given by -1, 2, 0, and we can write this as a linear combination of our pivot columns. In this case, we see that it's going to be -1 times 1, 0, 0, and then I'm going to add 2 times 0, 1, 0. We can recognize each of these as exactly our pivot columns. Now we know that U4 is a linear combination of the first column of U plus scalar weight 2 times the second column of U. Now we have an equation that relates the fourth column, second non-pivot column, to the two pivot columns. Oh, I'm sorry. Of course this should be the third column, because the third column of our RAF form was demonstrated to be our pivot. Okay, so now we have a linear combination of the two pivot columns that produce this non-pivot column. All of a sudden we can now move these over to the other side in the same way as before, and we write that in order to produce 0, we take a linear combination of these three vectors resulting in 0 right hand side. In vector form we see that this is 1, 0, 0 plus -2 outside of 0, 1, 0 plus 1 outside of -1, 2, 0. Of course, this adds up to 0 by design. We now do the same linear combination using the column partition version of a matrix, and we see that in order to produce 0, we multiply our matrix U by our second linearly independent solution, where I take 1 times the first column. Here I have nothing of the second column, so this whole second column I just cancel out by putting a 0 as a scalar weight. The third column I have a scalar of -2 in front. The fourth column I have a scalar of 1, and the fifth column I do not include in this linear combination, and we see that this linear combination produces the output 0, 0, 0. We now set the second linearly independent vector for the null space of our matrix to be this input, 1, 2, 1, 0, 2, 1, 0, -2, 1, 0. Okay. Finally, we find the last one, and we're going to do this one quickly by just looking at the columns of our RREF form. Remember, we're looking for an input vector that produces 0 just by taking linear combinations of the columns of U. Well, we know that this third non-pivot column, which happens to be the fifth column in general, can be written as a linear combination of these two pivots. In particular, we see that if we take a -3 times column 1 and we add that to 2 times column 3, we will get the negative version of this vector, which in particular, if we add -3 plus 3, we get 0. If we add 2 plus -2, we get 0. Here, these zeros come from the fact that we are not using non-pivot 1 and non-pivot 2 in order to produce 0. This is now what we call our vector Z3, and now we have all three linearly independent vectors for the null space. So with this, we say that the null space of our matrix U is equal to the span, the set of all possible linear combinations of Z1, Z2, Z3, which is also equivalent to the span of the vectors 2, 1, 0, 0, 0. The second vector that we saw was 1, 0, -2, 1, 0. And now the final Z3 vector that we just produced was -3, 0, 2, 0, 1. Notice that this is a subset of R5, which was our domain space. This means any vector in the null space can be written as a linear combination. So if Z is an element of the null space of U, that implies Z is equal to a linear combination of these three vectors. Further, because we can write U is E times A for invertible E, we see UZ equals 0 if and only if E times A z equals 0, which is true if and only if, multiplying by the inverse on both sides, we see that any vector in the null space of U must be in the null space of A. This now we can conclude immediately that this is also the null space of A. In order to find the null space, we do 3 steps. 1, we transform our original matrix A into RREF form. 2, we identify the non-pivot columns. For each non-pivot columns, we do step 3, which is to find the linearly independent vector corresponding to a unique solution to the homogeneous linear system. The span of these linearly independent vectors composes the null space. More on this in the next video.